The CC1352 embodies really all of the 802.15.4. The HC12 that we did, the other one, is really a subset. It's in the same general field of a sub-gigahertz platform, but not a full protocol. Obviously, one of the difficulties of any of this stuff is it gets complicated. And so either you go work for the company and you make new devices, or we basically architect with existing devices that are made to satisfy all of the rules. But again, we're still sub-gigahertz. And I'm going to, now the demo that I'm going to show you, where'd it go? I have a couple of demos here. Where'd they go? Are the demos I'm going to show you are not the 1352, but they're actually the 1310. It has the same 802.15.4 interface, but we'll get to the demo here in a moment. Okay. Now, 802.15.4 has really two categories: the sub-gigahertz and the 2.4 gigahertz. As we'll see coming up in the next couple of slides, 2.4 is where Bluetooth low energy and Wi-Fi exist. And so it's a pretty crowded channel. And so we're going to, for this lecture, end up in the 915 megahertz band. And notice there'll be channels, okay? These are small frequency limited bands of frequencies that are used for these channels. Okay.
How many channels are in the 2.4?
How many are there? A bunch. I got a figure in the, okay, so these are the sub-gigahertz channels. Yeah, I'm sorry, these are the 802.15.4 channels in the 2.4 gigahertz. In the BLE, which is obviously a couple of slides off, there are, yeah, this one. These are the same frequencies, and you can see there's 40 channels. There are 40 channels of BLE in that same band, and 3 channels of Wi-Fi. So in that same frequency, 40 bands of BLE, 3 channels of Wi-Fi, and 10 channels of sub-gigahertz. Is that the question you asked?
Yeah, so well, I guess is another question, but will they clash then?
Oh yeah, totally. Yeah, yeah, they will clash. Of course they will. If you transmit in the same frequency, one of the disadvantages of the stupid COVID-19 is you guys didn't try to do all your labs in the same room. Yeah, yeah. One of my problems when I get to my BLE demo is that there's so many BLE devices in my house, it's really hard to figure out which one's which, because I haven't really mastered the filter yet. I got to figure out how the filter works, and hopefully I will figure out the filter before I do that demo. No, they will clash. Hence the what do you do when they clash? Okay, so this is a 802.15.4 method for dealing with clashes. Okay, now it turns out the problem that you have, which is different than than when humans talk. Okay, when you and I are in the same room and I am talking, I can hear you talking, right? So if you are talking and I am talking, I can hear the collision. I may not care about it because I'm, arrogant and loud, but I can hear you talking while I'm talking. Whereas in this protocol, I can't listen, I can't sense the frequencies while I'm transmitting. Okay, I don't know, you guys are probably too young to have walkie-talkies. You push the button and you talk. Those, you also, when you push the button, you can't hear anybody else talking. And so the method of carrier sense multiple access collision avoidance is to listen on a channel for a little amount of time, okay? And if you don't hear anything, then send out a I'm busy, I'm using you, not actual data yet, okay? And then wait a little bit amount of time and then start transmitting, okay? And if that random amount, so if two devices are trying to speak on the same channel at the same time, okay, they will both listen, right? And notice there's nothing there, but since they will wait a different amount of time, and the sending a channel busy keeps somebody from jumping in, but the waiting the random amount of time means that the two devices will probably both work. Now, the performance measure, if you'd like, of this process is because there's a lot of waiting and a lot of listening and a lot of things. You can't use all the bandwidth, okay? You can't really use everything that's out there because it's not prescribed. In a high-speed CAN network, you prescribe who gets what, where, when, and you can get upwards to 100% of the available bandwidth usable. But in this context here, you're not expected to use all of the available bandwidth because of the randomness of the different devices all sharing the space. And so, these are numbers out of the textbook, out of the LEA textbook, that 20% channels will be useful if you can control the environment. The 26% and the 18% are not relevant. The point is, you can't use it all. Okay. Now, we have talked about the OQPSK encoding, and that's what this thing does. Okay. You'll see this over and over again. On the right hand side is the stack for sort of a general way in which people define communication layers. Here's what you got to know. What is define to me what a layer is. What does a layer mean to you?
Some abstraction in which we can think about a system.
Okay. Yeah, there is an abstraction. Sure. This is an abstraction. This is an abstractive thought. Okay. On the right, on the left is an actual, physical layer. And there's a mapping between the two. Obviously, from a topology standpoint, what do I mean by layer?
Or maybe
top to bottom, there's a sense of order.
Okay. So if you're in session 5, if you're in layer 5, session layer, who can you call and who calls you?
You can call down.
Yeah.
And then who calls you is everyone above you. Or
No,
the one layer above you, I guess.
One layer above, and so if it's a purely layered system, and we'll see that they break the rules all the time, but a layered system typically has, you can call down and you are called one up and one down, okay? Now, the advantage obviously is you can swap out layers. You can swap out a physical layer with a different physical layer, okay? Because nothing in 3 calls 1. 3 calls 1 and 1 calls 2, and at every barrier is essentially an application programmer interface, a set of API calls that you can use to, okay, so like I said, the physical layer is the 915 megahertz radio, and the physical layer and the you know, the MAC layer are implemented as something that's given to us. What does the word stack mean? It's not a LIFO, not a push pop stack. The word stack in this context means what?
Is it like the layers of software?
Yeah, the answer to the word is software layer, but it's also a physical layer. Okay, so in this context, stack and layers have similar context. Stack typically means software. Okay. Oh yeah. So I got some things. So what happens at the physical layer? We encode the symbols. If you remember back to the Shannon channel capacity thing, where there was a symbol rate. Okay. So every so many, so much time we encode a symbol. We modulate that using the OPQ FK. OP, that's a phase shift key right there. And then obviously it's demodulated on the other side. There is some synchronization that goes on here. And since there's a single antenna used for transmitting and receiving, the device typically switches modes between transmission and receiving. Here's an interesting thought question. Which takes more power, transmitting or receiving? There was actually a picture of this way back about a month ago.
Receiving.
Yeah, because you gotta, if you're trying to receive, you're often doing it. Now, the answer is it varies, clearly. But to transmit a packet typically takes less time to receive a packet. Because there's no, it's not like, it's not like SPI. There's no clock in there, or even I2C with a clock. So when it's time to receive, you basically listen and try to find it. And then obviously timing and acknowledgments. And we'll see acknowledgement packets. And then in the MAC layer is where it will look for error detection if you can correct it. And this is where the collision avoidance algorithm we just talked about. And we'll see beacons. Beacons are our way to perform. Beacons are a way to create the networks, to create the connections. Okay. And then the point of layers is there is an application programmer interface, a set of software functions that can be called. In this context, they're called SAPs, service access points. These are basically functions that higher layers can call lower layers to perform either data or control management. Okay. Okay. So this is a beacon based device, and the purpose here with the beacon is to prevent collisions. And so if you've got a beacon, we'll see that when we do the collector sensor demo, one of them is sending out beacons. And if you want to transmit, you wake up, listen for a beacon, and if you have a pre-allocated slot, then you count the certain amount of time slots after the beacon, and let's say you get guaranteed time slot 2, and then you can send your packet in slot 10, 11, and 12, time relative to the other. And so the whole point is, if you have control over the space, you can then use this beacon approach to preventing collisions. More, there's a link on the bottom that has a lot of information on the IEEE 802.15.4. There's a whole user's guide with way more information in it than the book has. This is obviously a picture from the book. And so the other way to communicate IEEE, you know, sub-gigahertz is to not have a beacon, and that just, you know, that just uses the carrier sense multiple access collision avoidance method. And then the question is, when you're listening, okay, when you're listening, how can you tell if somebody's talking, right? And here are, okay, it says 5 modes. Oh, using one or more, yeah. Some of the other modes are a combination of 2 of these. Is if you just look at the decibel level of the incoming waveform, right? Because you got a programmable gain amplifier on your reader. And so if your programmable gain amplifier is cranked all the way up to the highest gain, there's probably nothing out there, and you can sense it is not usable. And then these are basically other ways to look at whether or not, while you're listening, whether or not you can see, you know, is whether or not someone else is currently talking. Okay. Yeah, so the coordinator is the word that means the one sending the beacon. Okay, so you don't have a, beaconless means, or non-beacon mode is you don't have a coordinator. And so this is a topology for you know, sub-gigahertz, is if you have a pan coordinator, that's the one sending the beacons, okay? Then it's sending beacons, and it can, there are 2 things that aren't pan coordinators. They are reduced function devices and full function devices. Full function device could be a pan coordinator if it wanted to be. That's the over in the left-hand side, right? So these 2 here basically are the same physical. A full function device could be a pan coordinator if it wanted. And so if you have a coordinator, then sending out beacons, and then the device is attached to it. Whereas a reduced function device cannot send beacons. So it's typically lower power, and a reduced function device can only communicate to a pan coordinator. Okay. Whereas if you don't have a beacon, then the full function devices can form a network and talk to each other. So this is not, this circle here is non-beaconed. Okay. So again, the personal area network coordinator, the pan coordinator, is thing sending the beacons. Interesting. The packet didn't look like this when I sniffed it, but it approximately had this amount of stuff in it. You know, so I don't know. I mean, it's interesting to note that that it does have, you know, it does have a checksum. It does have a check character for looking for broken packets. It does have a variable length packet. It does have addressing info. You'll notice when I do the demo that there will be 2 addresses that exist in the protocol, the great big unique 64-bit media access control address, and then a short or local address, which is obviously simpler to remember. Okay, and when I do the demo, you'll see different kinds of packets, data, everything is acknowledged, beacon frames and command frames. Okay, so yeah, so the operation of join is when either a full function device or a reduced function device attaches itself to the personal area network coordinator. Okay, the PAN coordinator. Again, it may just be my sniffer that makes things look different, but anyway, let's go. Okay, demo. Okay, so here's my demo. All right, so I'm gonna stop share. I'm gonna stop sharing because it's working on the other one. Okay, now I'm gonna plug. Okay, I'm gonna do this. I got to allow myself to, while I'm fussing. Okay, so remind me when it's 15. Okay, so it's about 10:30. We started at 9:30. Okay, so good. Let me go. I got plenty of time for my demo. Well, let me put the thing back up so you can see what I'm doing while I'm doing it. Okay, so this is the sequence of events that I'm using to sniff. I plugged in a CC1352R, not a 53R. This is a 52. I don't know what a 53 is. No, 53. Pretty sure it's 52. Okay. All right. Duo. Okay, duo. Okay, that's good. That's good. That's good. Over here. Join. Today lecture start. Okay. Join. Okay. Join computer audio. Okay. So I'm now going to do these. Okay, leave computer audio, leave that open. Okay, so stop sharing here. And then allow multiple devices. Okay, so share over here. Oops. Skip that. Yeah, okay, good. Yeah, that's what we're doing. Okay, so I'll call that. Yeah, stop that. Yeah, all right. All right, so, oops, I need the thing to show me what I'm doing. Come back here. Oh, where'd it go? Oh, no. Yeah, Alt 10. Yeah, okay. Launch the sniffer agent. There we go. Launch the sniffer agent. This was fairly hard to install, and I do have it is paused right now because the sniffer agent somehow is running at deep in the system, and I have to. I don't know if you can see me type in my. No, you can't see anything. Good. All right. Never mind. You can't see what I'm doing, which is fine. I'm typing in my super user password. Okay, I remember what it is. All right. Okay, it's still waiting for me to be super user. There we go. I'm back. All right. All right. All right. So, like I said, I have the board plugged in. Okay. And so the next thing I'm going to do is choose the, oopsies, plug in, detect devices. Oh, it's a 1310. Never mind. Never mind. Wrong one. I got to plug in the 1352. All right, so I'm good. Okay. So I got my sniffer plugged in over here. Let me just relaunch. No, don't relaunch it. I have to go through this stupid thing again. Never mind. Should have just detected it. Hold on. You could be thinking about your project while I'm fussing with my demo. There we go. Device configuration. All right, so can you see device configuration? Choose the protocol. Okay, so I was doing a BLE last time, so I'm going to reconfigure it for, okay, where I think that one. All right, can you see? Yeah, can you see what I'm doing? Yes, you can. So these are the protocols that you can sniff. Okay, and so I have my collector sensor set of boards running at frequency shift key. Again, this is one of the sub-gigahertz channels. Okay. Okay, frequency shift key. No, that's still not right. Channel 27. That's not right. Selected channel. Oh crap. Trouble is I did this. 0. I made the wrong one. 50. All right. Start. Okay, this may not work. Okay. I don't know. I was playing with the BLE. Okay, so that's that step. The next step is I open Wireshark. I did install Wireshark 3.2 and that didn't work. Okay, so back over here. Okay, so plug in the collector. That's this one here. Okay. Okay, plug in the collector. Yeah. All right, where are we? Desktop. All right. So let me quit over here. Okay, so I got it started. All right. Okay, good. All right. So I opened a COM port on the on the other one. I'll show it to you in a moment. Okay. Cancel back. Okay. Launch collector, open terminal. Push button 2 on the collector to, yeah. Allow join. Oh, done something wrong. Rats. Running. Plug the other one in. Oh, there we go. Ah, fine. Good, good. All right. I just plugged in the sensor. Okay, so it's already connected. And so I'm going to disconnect and reconnect. Okay. Okay, so I do that with a, yeah, button 2 on the sensor. Okay, I'm going to push. These are, luckily for me, there's nothing else. There's nothing else in the room. And so, yeah, okay, I'll make this bigger so you can see it all. All right, so I'm going to push button 2 and disassociate. Okay, I think I did. You see, there's, okay, no, there's that button 2. Button 1. Oh, there we go. Button 1 to disassociate. So now I just disconnected from the network. If you notice, my my sensor used to be ID4, okay, and so I'm now going to push the other button, and associate again, and so so it requested a beacon. The sensor requested a beacon. The machine gave it to him. Okay, stop here. Just pause here for a moment. Yeah. And so right here, this happens when the sensor wanted to add. The sensor wanted to attach to the it was looking for a personal area network coordinator and did a beacon request. And then this is the beacon, the PAN coordinator, which says I'm a beacon, I'm a PAN coordinator. My address is AABB, okay? And then the MAC address, this guy right here, is the sensor's 64-bit MAC address, and it sent it to the coordinator saying, I would like to join. Association is a join. You can see there's an acknowledge, and then there's a connection, and then there's an association here. These two are connected, and now the sensor has been given a new 16-bit ID, okay? And so, interesting, this, okay, let me find if you bed in here, okay, there's the address of this is a data being sent from the sensor to the collector. No, this is the data being sent. Okay, that's right here. This is the data packet. Destination, no, that's the data. Anyway, this is the song and dance that the two devices are doing, yeah, this is a sensor. Here's a data. It goes from the sensor node to the collector node. The collector is the PAN area coordinator. Embedded in here, in these 148 bytes of stuff, is the protocol which contains the data, such as it is. Sort of interestingly enough, the size of this packet, these are like the preambles, the size 53 in hex is, and I get out my hex calculator. Is 35, and you see it right there. There's the length of the packet. So each of these packets, 3C is the length of this packet, 78 is the length of that packet. So that's the packet length there. There's the source address, there's the destination address, and these are 16-bit addresses. So this is the packet. All right, that's my demo. Stop share. Okay, don't they want to show over here? Anyway, so that worked better than I could have expected. Okay, so quit. Stop share over here. Share over here. You couldn't see both screens at the same time, but open up in this window is the terminal window for the terminal window for the collector. Okay, so what did I? Yeah, permit join on. Okay, it restarted while I was, okay, so that one. So this is what it normally looks like when you're pushing the buttons on the device. You know, not much, right? See, I pushed the buttons a couple of times and it rejoined with a different ID. All right. So when I run this, okay, that's another typo. I'll get this right. 1310. Okay. This thing will be useful if I figure out how to sniff Bluetooth. Right now, when I sniff a Bluetooth, it's really, really crowded I see everything. But again, my 1310 nodes are essentially the lab 1 gigahertz process, lab setup for the 1352. Just the 1310 doesn't do Bluetooth. All right, so I don't know anything about security, but this is a table out of the book that you can add security to it. And the more, and where capital N is little bit, a lot, and a lot of bits of encryption. So all these real devices, these are basically API calls that you can use to add encryption. Now, in my demo, you notice I didn't have to add the encryption key in. It was an option, but I was running it without encryption. And now just a couple of words about this particular 1352. Again, I don't want you to memorize any of these specs, but I want you to get a sense of how it is IoT is implemented. And I'm going to ask the question, in the CC1352, how many processors are there? I'm just warning you, I'm going to ask that question, okay? It's a big chip, you know, it's a Cortex M, that means it has floating point. It's gonna run TI-RTOS, as I showed you before. It's got flash. An interesting thing, now it turned out if you remember in your good old 319K days, the TM4C did this as well. There is a ROM on this chip and on the TM4C that we never told you about, but it has basically all the TI software libraries already burnt into ROM. And so if you're following along, this is a general thing that microcontrollers do, because ROM is fairly inexpensive to put on a, now this is ROM, this is not flash, can't be erased, it can't be programmed, it's real ROM. They download and install the full suite of software that this chip is certified for, and therefore you don't waste user space for system calls, okay? And so anyway, in other words, it has the TI RTOS, it has the IO drivers, the loader, this chip does BLE, it's got the BLE implementation as well as the one we're talking about now, IEEE 802.15.4. That entire media access control is programmed in ROM, okay, and not in flash. It has a second processor, and we'll show it, that controls the sensors. And it has a third processor for the radio, okay? Now, we're not going to do all of these, but we are going to, we're doing 802.15.4. We're going to do Bluetooth Low Energy, but it implements some of these other protocols. And the point of this slide is, gee, it's hard to make money in this space because you got to talk all the languages, okay? Yeah, these are all the protocols that this particular chip can do. And they're just trying to maximize their profit by, if you want more detail out of this whole chapter, rather than, the chapter 5 of the book, there's a whole book on this subset. There's a whole book on 802.15.4, okay? Which, as you remember, personal area network is you're not controlling necessarily all the devices in the room, but you're controlling all the devices on your network within the room. And it is long distance, low rate. That's the essence of this. This is the one that's going to be on the test. And that is in a typical implementation of a IoT device. When you buy a chip with a lot of features on it, how many processors are in there? In other words, how many instructions are being executed at the same time? I mean, I'm not talking about, multi-core, right? I'm not talking about a 16 wide core like you would have in an x86. I'm talking about independent program counters with very low bandwidth specific interfaces between them. And the answer is 3. This one has 3. The CC1352R has 3. I think the 3100 that we're going to do has 3. It has one processor that's dedicated to the physical layer, right? The thing that's attached to the radio, the thing that's attached to the antenna, and it's actual a processor that gets executed, okay? Now, yeah, there's a lot of analog front end to that, but it has its own ROM, which it means ROM, you can't change it, and its own RAM. Okay? So that implements the radio. Nobody likes TI-RTOS, so if you're doing data acquisition, you actually do your data acquisition here. This is your sensor interface. This is your I/O chip. And so it's got DACs and ADD converters and frequency counters, pulse width counters, touch sensors, those sort of things that all run in ULP. Can you imagine what that is?
Ultra low power usually.
Ultra low power, because this thing is not very fast, not very fast. And then these guys here are associated with that one. Okay, so there is a main processor. This is the one we program. Okay, This is the one that we connect to Code Composer Studio and program. But it's a Cortex-M with floating point, with lots of, so all of the I/O pins associated with this are there. But this is, again, the specifics of this particular chip are irrelevant, but the fact that there are multiple processors is a very common theme I see in these chips that implement. Now, when we did other labs, we added a fourth processor on top of it because we abstracted the whole, not for sub-gigahertz, but when we get the Bluetooth, when we see this same picture for the CC1352R, we'll add the MSP432 on top of it. So there'll actually be 4 processors. All right. Okay, so I showed you the packet sniffer. Okay, so I'm done with this, I'm pretty sure. Yeah, so what were you supposed to get out of here? You know, again, I don't want you to know any for the 1352 details. What I want you to do is that it's got multiple CPUs with well-defined interfaces. Okay, so, you know, the radio was over here, and this is the main controller, and this is the sensor. We talk about beacons. We saw a little bit about the, you know, about the avoidance. Okay. No, not stop share. Stop. Discord. Okay. All right, set up. Okay. Yeah, sure. I actually already showed you the packet sniffer thing out of order, and then I did my packet sniffing today. So, yeah, this is what. Yeah, so that's what I did that. Okay, so that's a good segue. And so, yeah, sure.